All right, I have some example for you. So I borrowed these reactions from a textbook by Clayton. Okay, and so if you don't have this textbook, don't worry about it. But I think they have pretty good explanation. Let's take a look on this for reaction. Okay, all right, the top two. These are all Vedic reaction. Okay, all these are Vedic reactions. So we have Ylid react with an aldehyde. You know, we have Ylid here react with an aldehyde down here. All right, Ylid here react with aldehyde here. Ylid here react with aldehyde. All right, so this is all Vedic reaction. But the top two, the stereoselectivity go to Z isomers. The bottom two go to E. And here's the explanation. Okay, the type of Ylid matters. Well, what do you mean by type? I haven't talked about type yet. Oh, let's take a look. So there are two types of there are two general type of Ylids. The number one is we call unstabilized Ylid. Okay, what do you mean by unstabilized? Well, that negative charge on Ylid carbon is practically localized on that carbon. You can say you can draw a resonance structure to phosphorus, so that's delocalized to phosphorus. But well, actually, in this case, that the negative charge just stay on the carbon. Okay, we call it unstabilized Ylid. The other one we call stabilized Ylid. Now, this one you can actually see is stabilized by the carbonyl carbon next to it. You can even draw the resonance structure there. All right. So basically, this the stabilized Ylid has electron withdrawing group on it and conjugated with the double not the bond, the lone pair of an Ylid. All right. So there are two types: unstabilized Ylid and stabilized Ylid. The unstabilized one favor the formation of Z, selectively make Z. The stabilized one, right, on the other hand, favor the E isomers, selectively make E isomers. Okay, and here's the reason behind it. Let's take a look at the first one. This one is unstabilized Ylid. Okay, so negative charge right there, not conjugated with the carbonyl next. There's no carbonyl next to it. So this is unstabilized Ylid. This one react with the aldehyde, favor the formation of Z isomers. Okay, 91% go to Z isomers. All right, here's the explanation behind it. Let's take a look. So here's the, I'm going to draw a carbonyl carbon, a carbonyl compound like that. Look like C double bond O is pretty long. Okay, that's the reason why I do that. You will see. You will see. All right. All right. So make sure you understand how this is how I will communicate with you in the next few slides. Okay. So we have a carbonyl look like that, and I think you guys know that alkyl groups have some steric hindrance. Okay. Oxygen contains quite a lot of electrons, so high electron density up here. So have some electronic repulsion. Okay. All right, so let's try with me. So this is my like how I draw. Next one, the Ylid reagent. Okay, so I draw C double bond P pretty long. All right, you will see why. Now, the top part right here, this is Ylid. So triphenylphosphine on the top right here, the triphenylphosphine is too big. So instead of drawing like this every time, I mean, it takes a lot of energy. So I'm gonna make just an umbrella, right, to represent triphenylphosphine group look like this. Are you guys okay with that? Make sure you know this is high. This is a lot of electrons up here. All right. All right. So this is my Ylid reagent. Alkyl group right here, of course, got steric hindrance. All right. But the phosphine, triphenylphosphine up top here, of course, have some steric hindrance. But since each benzene got a lot of p orbitals, right? Pi electrons, so electronic repulsion, big electronic repulsion at the top right there. Okay. All right, I'm going to make aldehyde in this case, or ketone. Aldehyde react with an Ylid. All right. So these two, you guys know the collision theory. So the any reaction that occur, all the reactant have to collide in the right angle. All right. So I'm going to show you where the right angle is. So first of all, this is not the right angle, and here's the reason why. Too much electronic repulsion, right? A lot of triphenylphosphine, big pi electrons in here. Oxygen, also a lot of electrons, so there's a not good, they repel. So they can't just react like that. All right, so electronic repulsion. Can't do it like this either. Well, it looked good because there's no electronic repulsion at the top, so it worked for the phosphorus. No electronic repulsion at the bottom, work for oxygen, right? So it should fit well. But if you remember, we're trying to make oxaphosphetane, where phosphorus and oxygen we're about to make bond. This is not going to make bond right there. Oxygen and phosphorus, they have to line up perfectly, right? This isn't just like oxygen point down, phosphorus point up. They're not going to meet. So can't work either. Well, if you can do parallel like this, the other option is you have to be perpendicular. Okay, they have to collide perpendicularly. Is that a word? Perpendicularly. So, all right. Now, this possibility of the angle that they can collide, right, perpendicularly. The one we have alkyl group together, alkyl group far away. But let's take a look at. I'll have you take a look at this. Which one do you think? And then no, they repel or it's not gonna work. The first one, you should see the first one, alkyl group and alkyl group get really close. Nah, that doesn't look good. The transition state is gonna be really high in energy. So this is too slow. Okay. Now I'm gonna flip the alkyl group to the top. Look like that. There's an alkyl group at the top, closer to the triphenyl phosphine group. What do you think? Steric hindrance, right? And triphenyl phosphine have a lot of electron density, big pi electrons, so it's gonna repel with the alkyl group. Not good, all right? Now, the third one though, what do you think? An alkyl group right here with a hydrogen, right? Oxygen, electronic repulsion, but it doesn't really get close to the triphenyl phosphine, so it's actually good. I like that one. Right? So the transition state should be somewhat stable or more stable than the previous two. And the last one where we got an alkyl group really close, so I just flip the third one, flip alkyl group up. This alkyl group is too close to the triphenyl phosphine group, so nah. Okay, so the best confirmation, the best angle that these two, the aldehyde ketone and ylid will react is right here. I'm gonna take just this guy right here. That's the best angle. All right, and then the rest gonna be drawing the mechanism. So we're gonna make the four-membered ring. So take the oxygen, use the not lone pair, use the pi electrons of attack phosphorus. Look like that we drew this together in the previous slide, our previous video. Okay, so oxygen attack phosphorus, and then carbon of the ylid, carbide, actually there's a carbon ion, attack the aldehyde. So oxygen attack phosphorus, and what's that? Carbon ylid right here, attack the carbonyl carbon. Here we go. You're gonna make a four-membered ring look like that. All right. Don't get confused. I haven't changed any position yet. I just want to keep it like that. So basically, I'm just form bond, phosphorus and oxygen bond, and then carbon bond look like that right here. This bond here and this bond here. Okay. All right. This is actually a cis or Z isomer. You'll be like, no. Are you gotta be kidding me? Where's cis? I can't even see cis right there. Well, hold on. Think about it. The intermediate oxaphosphetane form a four-membered ring like that. And you guys know the four-membered rings kind of flat. It's puckered a little, but it's kind of flat like that. All right. This is not really a flat four-membered ring. See that? So what's going to happen? Well, this bond's about to rotate clockwise. Now, this bond about to rotate clockwise. The oxygen will move and line up with phosphorus. All right. I'll say one more time. Just make sure you guys get it. The oxaphosphetane is a four-membered ring, and a four-membered ring kind of like all four atoms are lined up. Now they line up. They what's the word for it? Eclipse. I can't really say eclipse. They line up perfectly. All right. So, but this I haven't changed anything yet. So oxygen and phosphorus have to line up. So what's going to happen? This the carbon bond right here will rotate clockwise, move oxygen up, pair up with the phosphorus. And when that happens, the other atoms have to rotate, follow oxygen as well. So if oxygen go toward phosphorus, go that way, hydrogen will go replace the alkyl group. The alkyl group go replace oxygen. Look like that. That's cis. That's a Z isomer. Do retro 2+2 retro disorder, not disorder, retro cycloaddition. That's you get Z isomer. Okay. All right. Next one, we're gonna use stabilized Ylid, and I'll show you how we get E isomer.